What's up, everybody? I want to show you something kind of crazy. When I first heard about this, it really bothered me, so if you have that reaction, it's natural, but I'll help you get over it, and it'll hopefully make sense by the end of this. The crazy thing is this: if you've got an object, say this ball, say this is a bouncy ball, and it's going in a straight line, it can have angular momentum. And I'll say that again. A ball traveling in a straight line can have angular momentum. When I first heard this, I was like, what? There's no way this ball can have angular momentum. It's moving in a straight line. It's not even rotating. Don't things have to have some sort of rotational motion in order to have angular momentum? And it turns out they don't. But the proper response, it gets a little weirder. Before I show you how it makes sense, let me show you this. It doesn't even have to have angular momentum. It could be that this has no angular momentum. And before you get really confused, let me explain. The proper response to someone saying, does this ball have angular momentum, is to respond with angular momentum about which axis. So you have to specify the axis. So the axis is the point about which you're going to consider the rotation. So if I said, does this ball have angular momentum? If the ball is moving in a straight line, does it have angular momentum relative to this axis? That's a proper question. But if I just ask you, does this ball have angular momentum, and don't specify the axis, then it's not even a meaningful question. So let's try to figure this out. Why does this ball have angular momentum at all, regardless of any axis, right? That's the confusing part. It's not even rotating. How does a ball moving in a straight line have angular momentum? We know it has regular momentum because objects with mass and velocity have momentum, but it's not even rotating. How can it have angular momentum? First, let me explain conceptually why that makes sense. So imagine you have this bar here, right? And this bar, say this is a bird's eye view. We're looking down. This bar is attached to an axis that can rotate, and we're looking down. This is on a tabletop. Let's say this is all happening on a tabletop, and we're looking down at it. So imagine we throw this ball, right? This ball, moving in a straight line, hits the edge of this bar. And this bar, what is it going to do? We know what it's going to do. It's going to rotate. It's going to rotate about its axis. And now the question is, this bar initially had no angular momentum because the bar was just sitting here at rest. Then it did have angular momentum after the ball hit it, right? Because objects rotating around in a circle have angular momentum. Where did this bar get its angular momentum? Well, the only thing that bar interacted with was this ball. So this ball must have come in and transferred some angular momentum to the bar, because where else would the bar get the angular momentum from? I mean, if we believe in conservation of angular momentum, that angular momentum has to come from somewhere. It can't just pop out of nowhere. So the only place that angular momentum that the bar got had to be from the ball, because that was the only other thing in the problem. So this ball had to come in with its own angular momentum, even though it was traveling in a straight line, which is kind of weird, but that's the case. That's physics. And that's also why it makes sense why it depends on where the axis is. Because if I take this bar and I move this bar over to here instead, right? So now we consider our axis over at this point. Well, imagine the ball hitting the bar at the axis point, right? It just hits right there, boink. It's not even going to cause that bar to rotate because it's hitting it at the axis. So the location of the axis is going to determine how much angular momentum an object has that's moving in a straight line, because if it hits this bar at the axis, it's going to transfer no angular momentum. But if it hits this bar far away from the axis, it can transfer a lot of angular momentum, because the bar is going to rotate a lot, because there was a large amount of torque applied, since this force was applied at a distance that was far away from the axis. Now, you still might not be all that impressed. You might be like, that just sounded like a bunch of physics witchcraft to me. How do you calculate this exactly? How do you exactly define what we mean by the fact that this ball has angular momentum? So let's define this exactly. Let's say this ball has a speed or a velocity v, and the mass of the ball, we'll say the mass of this ball is m, and the distance from the axis to the ball, let's just draw that on here. So that's going to be from the axis to the ball, we'll call that little r. And now we can define precisely what we mean by the angular momentum of a point mass. The angular momentum of a point mass, L is the symbol for angular momentum, is going to be m, the mass of the ball, so the mass of the object that has the angular momentum, times v, the speed of the ball. And this is looking pretty familiar because m times v is just momentum. So this is regular momentum. But if you just left it like this, that'd just be regular momentum. We have to turn this into angular momentum, and we do that by multiplying by r. And r is defined to be the distance from the axis, or your origin, to the mass that you're considering. And so this is the total distance r, but you're not done yet. You need one more term in here. That's going to be sine of the angle. Sine of the angle between the velocity and the r vector. So you're going to have sine of this angle right here, the angle between the velocity and the r vector. Now I'm being a little sloppy, so people paying attention out there that already know this might be a little concerned. Technically, r goes from the axis to the mass, so this isn't the angle between v and r. Technically, you have to imagine r being extended out this way, and then that's the angle, but because we're taking sine of either of these angles are supplementary. The sine of either of them are going to give you the same number. So you're safe by just taking any angle here between v and r, and you'll get the right answer. But this is complicated. If I were you, I'd be like, oh man, mvr sine theta, I don't want to have to figure out what the angles are between things. And you don't. There's a trick. So check this out. If you just consider, what does r sine theta even mean? What is this, right? Visually, what does this represent on here? Well, here's the total amount r. Here's theta. Think about it. R times sine theta. Imagine making a triangle out of this. Make a triangle that goes from there to there, and then here to here. So you've got this triangle here. R times sine theta is just this right here. So it's just this length right here, this opposite side. Because, all right, if you didn't catch that, that might be a little bit weird. So sine of theta is always opposite over hypotenuse. And our opposite side, opposite to that angle, is just r. So that's just r. And then the hypotenuse, is just this little r, this pink r. I'm going to call that little r. So if I multiply both sides by little r, I'll get that r times sine theta. And this theta here is this theta here. So this is that theta right there. R sine theta is just equal to this right here. And what is this? This is just this point of closest approach. So when the ball makes it to this point right here, when the ball gets to this point, going this way at some speed v, it's going to be r away. So all you really need to do to find the angular momentum of an object, of a point mass, even if that point mass is going in a straight line, is take the mass times v. And then if you don't want to have to worry about sine theta and all of that mess, just multiply by r, which is the distance of closest approach to the axis. So that's what this r is. This r is the distance of closest approach to the axis. And that's just this right here. That's just this distance right here between the axis and the point where the ball will be closest to the axis. So that's this distance right here. Turns out this r sine theta is always just equal to that. So you can make life easy. Just imagine when this ball comes in, at what point is it closest to the axis? That would be this point. And then how far is it when it is closest? That gives you this r value. You can take mvr. That gives you the angular momentum of this point mass. Tells you the total amount of angular momentum that thing could transfer to something else if it lost all of its angular momentum. That's how much angular momentum something like that rod could get. So let's try an example. Let's do this example. It's actually a classic, a ball hitting a rod. Man, I'm telling you, physics teachers and professors, they love this thing. You should know how to do this. Let's get you prepared here. So let's say this ball comes in, it hits a rod, right? And so the ball is going to come in, ball is going to hit a rod, and let's put some numbers on this thing so we can actually solve this example. Let's say the ball had a mass of 5 kilograms, it was going 8 meters per second, hits the end of the rod, and the rod is 10 kilograms, 4 meters long. And let's assume this rod has uniform density. So this rod has a nice mass distributed evenly throughout it, and it can rotate around the end. So when the ball gets in here, strikes the end of the rod's going to rotate around its axis. And let's make another assumption. Let's assume when this ball does hit the rod, the ball stops. So after hitting the rod, the ball is stopped and the rod moves on with all the angular momentum that the ball had. That'll just make it a little easier. We'll talk about what to do if that doesn't happen. It's not that much harder. But let's just say that's the case initially here. So I move the ball back over to here. How do we solve this problem? Well, we're going to try to use conservation of angular momentum. We're going to say that even though there's an axis here exerting a force, the force that axis is going to exert on our system is going to exert zero torque because the R value, right? Torque is equal to RF. sine theta. And if the r is 0, r is the distance from the axis to the force, if r is 0, there's going to be no torque exerted by that axis. And if there's no torque exerted externally, there's no change in angular momentum of the system. So this system of ball and rod is going to have no external torque on it. That means the angular momentum has to stay the same. This is a classic conservation of angular momentum problem. So we're going to say that L initial, the initial angular momentum, has to equal the final angular momentum. And we just say, for our entire system, what had angular momentum initially? Well, it was this mass. So this mass had the angular momentum. And how do we find that? Remember, it's m times v times r, and the r is that distance of closest approach. So we're going to use this here for the whole 4 meters as this r. Yes, you can consider this hypotenuse r and the sine of the angle, but that's harder than it needs to be. You can find angular momentum with mvr. That's going to equal the final angular momentum. Remember, this ball stops. So since this ball comes to rest and it's only the bar that has angular momentum afterward, we only have to worry about the angular momentum of the bar on the final side. And to find the angular momentum of an extended object, a rigid object, you can use I omega. And this would let us solve for what is the final angular velocity of this rod after the collision. So that's what we want to figure out. What is the final angular velocity of the rod after the collision? Now we can figure it out. We know the mass of the ball, m. We know the speed of the ball initially. We know the r, line of closest approach, that's 4 meters. What's the moment of inertia here? Well, it's just going to be 1/3 ml squared. Let me clean this up a little bit. Let me take this. I'll just copy that, put that right down over here, and we can say that the moment of inertia of a mass of a rod rotating around its end is always going to be 1/3 ml squared. So 1/3 times the mass of the rod times the length of the rod squared, which is going to be the same as this r here, because this ball's line of closest approach was just equal to the entire length of the rod since it struck it at the very end, and then times omega. So we can solve this for omega now. We can say that omega, I'm going to bring this down around here so I've got some room. Omega final of the rod is just going to be what? It's going to be mass of the ball times the initial speed of the ball times the line of closest approach, and then I'm going to divide by 1/3 the mass of the rod times the length of the rod. I can just call that r. It's the same variable, length of the rod squared. And that's what I get. So I can cancel off one of these r's. And then I can plug in numbers. If I wanted to actually get a number, I could say that the final angular velocity of this rod is going to be 5 kilograms. That was the mass of the ball. Times 8 meters per second. That was the initial speed of the ball. And then I'm going to divide by 1/3 of the mass of the rod was 10 kilograms. And then the length of the rod, which is this line of closest approach, was 4 meters. And if you solve all that, you get 3 radians per second. So that's how much angular speed or angular velocity this rod had after the ball hit it and transferred the ball's angular momentum into the rod, giving the rod angular momentum, causing it to spin around and rotate at 3 radians per second. Now, what would be different if, instead of getting stopped, the ball bounced backward, let's say at 2 meters per second? Well, now the final angular momentum wouldn't just be the angular momentum of the rod. You'd have to include the angular momentum of the ball. But here's the tricky part. If the ball was coming in this way initially, which would mean it has angular momentum essentially around this way, and the ball went backward the other way, now it has angular momentum around this way, you would have to have a negative sign in here. In other words, when you include this angular momentum on the right-hand side, you'd have to treat it as, well, there's a couple ways you could do it. You could just do plus if you wanted to, and then you do the mass of the ball times this -2 meters per second times the same 4 meters as the line of closest approach. You could put the negative here with a plus out here, or you could put the negative out here with a plus in here. You could do it either way, but this term for the final angular momentum of the ball would have to have the opposite sign as this term for the initial angular momentum of the ball. So recapping, a ball can have angular momentum even if it's moving in a straight line, and you could determine the angular momentum of that ball by using mv r sine theta, where r is the distance from the axis to the point where the ball is, and theta is the angle between r and the velocity. Or if you don't want to use r sine theta, you can use mv capital R, where this capital R represents the closest that ball will ever be to the axis as it's traveling along its straight line.